Thank you, Steph, and thank you, RSC, for the invitation. As a mechanical engineer, definitely a strong sense of imposter syndrome here today. So, no chemistry questions, please. And any library that can have 7 volumes on water. Wow, that's impressive. And I'm sure there's lots of other volumes on lots of other interesting things. So, what I'm going to talk about a little bit, and you will learn as I go through this that I'm from an energy background, as I said, mechanical engineer. So I'm going to focus very much on an opportunity that may or may not exist for alternate materials to those that are PFAS derived or fluoropolymers, if you like, an opportunity in the market should there be a ban or a partial restriction on PFAS. So we'll move through this quickly. Very quickly, a little bit about AMI. The acronym stands for Applied Market Information. That didn't help me anymore when I started talking to AMI. Essentially, what we do is we help the plastics industry. We're very much a niche organisation. We work with the plastics or polymer industry, innovate and grow. We provide business critical information and networking platforms, events not dissimilar to this, for example, and market intelligence products containing market information and opportunities. These are a quick sample of those reports. You'll get access to this presentation, and this is the current report that I'm working on, as I say, examining the opportunity of alternates. A little bit of background, and I think we all know why we're here. We're looking at the potential for a ban on PFAS and PFAS-related products. One thing that stands out is that the EU has tended to bunch the small molecular chain materials with the long chain materials, so it immediately encompasses polymers and fluoropolymers, which, as we're going to talk about today, could be rather awkward for certain industries without particular replacements. I'm going to digress a little bit and talk about net zero and the drive towards it, and you may wonder why I'm going to go there, but in terms of achieving net zero, between now and 2050, there is a projection that the use and demand for gas is going to increase significantly. And associated with that, as countries, I should say, demand more energy independence, the demand for LNG is going to increase too. I've picked these data simply because I'm going to use a couple of examples to illustrate the effect that a ban may have as I move through this presentation. And then finally, looking at the liquid side of the hydrocarbon production, oil demand itself is actually going to decrease because essentially the move towards electrification that comes with the attempt to get to net zero. The blue lines on each of these charts represent what's required to hit the 2050 net zero targets, but the reality is, and I think it's beginning to be accepted around the world now, that is an aspiration rather than something that may be achieved, but we shouldn't stop trying. So one unintended consequence of a ban on fluoropolymers, and I'm just picking this as an example, as a potential opportunity, is the application where ships use fluoropolymers in their stern tubes. A lot of stern tube lubricants leak into the environment. Here we've got an example of up to 61 million litres. Now, without fluoropolymers in those stern shafts, that volume could increase, in fact. Also, the use of fluoropolymers becomes more important because of the environmentally accepted lubricants are potentially more aggressive. So we're heading down the line of needing those more chemically inert materials to be used. I would point out that I'm here as a neutral. I'm not here to promote a ban. I'm not here to promote applications and usage. I'm just pointing out some opportunities and some potential issues that may come along. To name a few other applications, we've got in the oil and gas industry or in the energy industry, hacker elements, cavity pumps, yada, 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 thermoplastics used in flow lines, so your PVDFs, this kind of thing. A lot of materials are going to be required to be replaced and alternatives are going to be required. So why do we use fluoropolymers? Again, you know, I've indicated they're chemically robust, they operate at high temperatures, nothing new to you guys in the room, I'm sure. But this is an example of an elastomer selection guide. There are many around from different suppliers. Admittedly, the selection of chemicals here has an on-field bias, but as we move along the top here, where we're looking at different polymer types, you can see why people do specify fluoroelastomers and perfluoroelastomers, because they're green and they're safe to use. And if you work on that basis, of course you're going to use that because you've done your risk analysis, you're going to go down that route. The reality is there are alternatives because no one in the oilfield industry uses all these materials in this combination. So we heard about a little bit more earlier on about qualification and standards. If you qualify to the application, you could possibly use existing alternatives, but that doesn't always happen. This is a belt and braces approach here. And of course, people want to sell you their best and most expensive rings. Now this problem, that's from the supplier side. If we look at the end user, and I used to work for one of the energy providers, they are as equally responsible for this, if you like, over-specification of materials. So this is the guidance from one of the energy providers on selection of materials. So again, you see the chemicals, unfortunately the table's ran the other way, but the chemicals this time are along the top. We've got temperatures, and again, you're being driven down the route of fluoropolymers, fluoroelastomers. But again, not all of these chemicals would be used in combination. So, you know, you could work hard and do a little bit more qualification and find alternates. There are existing alternatives out there. And far be it from me to talk about chemistry, and I'm not going to. The issue really revolves around solubility parameter, as we know, and how much the materials react with contact with a particular fluid or chemical. So we've got various material types here, and the key takeaway is that the fluoropolymers react pretty neutrally across the range of solubility parameter, whereas, for example, if I picked an EPDM, it's going to swell, or mass equilibrium, if you like, uptake is at 160% here for solubility parameter that may be around something like diesel fuel, something like that. So you've got to choose your materials carefully. And that, again, this is why people tend to head towards an FKM type solution. So can we just replace these with something else? It's possible, but the evolution of these materials has taken many years. Again, harking back to some of the earlier presentations, qualifications for these applications are going to take a long time, and I've got a couple of examples coming up. They can take upwards of 2 years, the qualification programs. They will need potentially a whole new, if you like, suite of materials. So one of the messages that I want to pass on is that we need to start now. These alternatives, we've got to start looking for them if we're going to be able to hit any kind of replacement requirement that the regulations may lay on us. I'm peering hard at my timing here, and I have to move quickly. So here's an example of a qualification program, flexible pipe. They typically might use elastomer and perfluoroelastomer seals, but also PVDF in the linings. This is a recognised industry standard. It does not, as was perhaps indicated earlier, these standards do not specify material types, they specify the tests that are required to qualify the materials. And that's an important distinction. Typically, standards will not tell you which material to use, they tell you how to qualify them. And one thing of note here, this is a 226-page document, and these tests will take upwards of 2 or 3 years to obtain, to reach qualification. For an O-ring, you could use an Arrhenius approach, but again, accelerated aging of an elastomer, particularly a perfluoroelastomer, is like, it's designed not to age. So how do you qualify this material? So again, there's a lot of background work to be done here. And in terms of the market value, I saw, I think, some numbers for the UK market. I think it was, forgive me if I'm misquoting, but I think it was around, the upper level was about 1.6 billion. Looking at just the fluoropolymer market, the value in billions in US dollars currently is around 8 billion, projected to increase to 13 or 14 billion. So to me, that says there's an opportunity. I don't know how many suppliers or manufacturers we have in the room, but that says it screams opportunity for me. And again, you do have access to the slides because this may be a bit busy, but it gives some of the applications that you can see there. So it was a very quick whistle-stop through these slides, whistle-stop tour. Quickly, let me read through these. So PFAS-derived materials are seen as critical to the industry, and there'll be people in the room that are telling you that they can't work without them. But they are currently the only option available for many applications. However, end users have a part to play, and with risk analysis and risk aversion, people are always going to be tending to over-specify. Other materials are available, and with that over-specification in mind, we need to persuade people that maybe they do need to look a little harder at those specs and maybe try and qualify something else that might be available just now. The work for replacements needs to start now because of the time required to qualify materials. I'm not going to get bogged down in the LNG stuff because that's rather a specific example. So I'm going to stop there, Steph.